Oh, hey, Charles.
Hi, Michael. How are you doing today?
I'm doing well, thank you. How are you?
I'm doing just fine. Thank you so much for asking. But I do have a question.
And what is that?
Why are we here?
Why are we here?
Why are we here?
Because we're teaching a class on reinforcement learning.
But we've already taught a class on reinforcement learning.
We taught a class on machine learning, and there was a section of that class on reinforcement learning. So it was a kind of a mini course.
Okay, but we've done this already, so why would we be doing this again?
The idea was that when we were doing the mini course last time, there was all sorts of topics that we didn't get to go into depth on, and it's a topic that's really interesting to us. So we thought we could just kind of expand it out into a whole class.
Okay, that seems reasonable, but you haven't convinced me yet that this is really a whole class and that we're doing something different. So what are we doing this different?
So, well, mostly we're going to just be going more deeply into the theory and practice of reinforcement learning.
Okay, well, half of that sounds interesting.
Oh, good. So on the theory side, we're going to be studying things like the convergence of algorithms, how long it takes them to converge, whether you can put bounds on how many mistakes it's going to make before it converges, situations in which you don't have convergence. These are all sorts of really... you don't want to hear so much about that.
Oh, are you talking? I'm sorry. What about the practice side?
All right, so on the practice side, we're going to be doing a lot more in terms of implementations of reinforcement learning algorithms, and we're going to do, for each lesson, some kind of exercise where we use a system that we built called burlap. The sorts of topics we're going to talk about include things like temporal difference learning, like the TD lambda algorithm.
Oh, I like TD lambda. I actually did a thesis on that once.
Oh, nice. Okay, good.
Exactly
So
once.
you should, okay. So you should be interested in hearing about that, or maybe even talking about that. We're also going to be talking about how you can express things using reward functions, which is a really important topic in reinforcement learning because all of the way that we communicate with the algorithms is in terms of their incentives in the form of rewards.
I like that. That makes a lot of sense. It's sort of the practical things that matter about making reinforcement learning actually work in the wild. Let's do that. I like that. What else?
We should be talking about generalization and scaling to some degree.
Oh, I like that. I want to talk about generalization and scaling, and I want to tie it back into abstraction.
Oh, that's a really important topic. Great.
Okay, cool. Can I do that?
Sure. Why don't you do that piece, and I'll talk about partially observable Markov decision processes, which is decision making when you don't have complete knowledge of what the current state of the environment.
Okay, that seems reasonable. I'll trade you. You can do POM-DPs if you let me do options.
Okay. All right.
And Monte Carlo methods.
Okay, it's a deal. But we're also going to talk about game theory, which is awesome because it has theory right there in the name.
Okay, that's true, but it also has game right there in the name, and that's what makes it cool.
It should be fun for everyone.
Yes, fun for the whole family.
So in the game theory section, we're actually going to harken back to things that we did in the previous mini course, but then we're going to update it by giving more details about different solution concepts.
Oh, right, that's right. Last time we did this class, we talked about all these things besides Nash equilibria that were really interesting, and so we're going to have a chance to talk about that now?
Yep.
Good. So can we do correlated equilibrium?
You can do correlated equilibrium.
I'll do correlated equilibrium. Sounds good.
All right, so are you ready to go?
I think I'm ready to go, so let's go.